Yes, thank you for coming. My presentation is about the hydroxyapatite-coated porous magnesium for biomedical applications. First, I'm going to tell about why we are trying to use the porous magnesium as a fabricated porous magnesium is that because magnesium has very many good features as a biomaterial, such as it is a very light compared with other biometals, and it is an essential element for human metabolism. And most of all, it is biodegradable, and it has a higher strength compared with other degradable ceramics or polymers. And it has a similar elastic modulus with that of the bone, so there's a less possibilities for the stress shielding effect to happen. So if we make this magnesium into porous structure, the cells would easily go inside the pores and fix the implant with the surrounding tissues. And also, due to the blood flow through the pores, healing would be much faster. But there's some weakness about this porous magnesium is that first, one of the methods to make the porous structure is the powder metallurgy. But because of the high reactivity of magnesium powder has an oxide film on the surface, so it acts as a barrier for the diffusion during sintering. And another most big reason is the magnesium corrodes very fast. So in the aqueous solution, so it is hard to use, and during the corrosion, the strength decreases and hydrogen gas evolution happens, which hinders the cell attachment. So to solve these problems, we use spark plasma sintering to sinter porous magnesium, and we coated this porous magnesium with hydroxyapatite by the aqueous treatment to improve the corrosion resistance and biocompatibility. I divided into two parts. First, the fabrication of porous magnesium, and second, the hydroxyapatite coating part. First one is the fabrication of porous magnesium by spark plasma sintering. This is the, I'm going to talk about spark plasma sintering first, which we call in SPS. This is the brief design of the SPS. We put the powder inside the copper mold and press it in a low vacuum state and give a pulse DC current to start the sintering. And due to the pulse DC current, the sparks and Joule heating occurs between the powders, and it makes the sintering starts. There are some advantages of this SPS, such as fast heating and cooling rate is possible, and the sintering occurs in a very considerably low vacuum state. So it has a shorter process time compared with the general vacuum furnace. And the more important aspect is that sparks occurs between the powders, which destructs the oxide film on powders and helps the sintering occurs. So this is a brief design experimental procedure of my work. We mix magnesium powder and sodium chloride powder. We use the space holder method and with the sodium chloride as a spacer. These are the SM image of them, and after mixing them uniformly, we put them inside the copper mold and press it with 20 megapascal pressure, and then we gave the pulsed DC current. This is the brief condition of our experiment. We increased the temperature up to 585 degrees and maintained for 2 hours. And to make the porous structure, we tried to dissolve the sodium chloride, and so we put the specimen inside the sodium hydroxide solution because magnesium itself has there's a limitation of corrosion at the solution which has pH higher than 12. And to dissolve sodium chloride much faster and completely, we use the vacuum pumping to put the solution inside the pores more easily. This is the bare porous magnesium with 60% porosity, and this is the XRD result before dissolving sodium chloride and after dissolving sodium chloride. As you can see, sodium chloride peak disappears and the only sharp magnesium peaks can be detected, which means that sodium chloride has been dissolved and magnesium has been sintered without any oxidation or carbonizations. These are the porous magnesium with different porosities, 70, 60, and 50% by changing the volume ratio of the sodium chloride. And this is the microcity result of them. And as you can see from the microcity, there's a very good pore interconnectivities and almost near complete dissolution of the sodium chloride. The average pore size of the porous magnesiums had almost 40 micrometers, and you can change the pore size by using different size of sodium chloride. And these are the SM image, surface SM image of the porous magnesium, and you can see that it has a very, good pore interconnectivities. And with the higher magnification, you can see that magnesium has been well sintered without the visible boundary of the magnesium powders. And now is the hydroxyapatite coating part. And as I mentioned before, corrosion is one of the biggest problem of magnesium. And because porous magnesium has a much more surface area than dense one, the corrosion occurs much faster. So we try to coat hydroxyapatite coating by aqueous treatment introduced by Hiromoto's group. Hydroxyapatite, which we call HA in short, is a main component of the human bone, and it has a good biocompatibilities. And it has been already used commercially as a biomedical applications. And this is the simple principle of our the HA coating. If we immerse the magnesium inside the solution, which has calcium source and potassium phosphate source, the magnesium corrosion occurs, and on the surface, pH increases. And so because of that, the hydroxyapatite forms on the surface, and it grows as a needle shape. And this is the procedure of the HA coating. We make the solution by dissolving calcium EDTA and potassium phosphate and increase the solution up to 90 degrees. After that, we put the porous magnesium inside the solution and also use vacuum pumping to put the solution inside the pores more easily. And after several hours, we take out the specimen and cleanse it with the distilled water. And after the coating procedure, the porous magnesium color changes to the light black. And by the X-ray result, you can see that hydroxyapatite has been formed on the surface of porous magnesium. And we check the compressive strength and stiffness of the porous magnesium with different porosities. As porosity decreases, you can see that strength is increasing, as everyone would know. And as you can see from the data, porous magnesium was not brittle but ductile, which we wanted. And after coating with hydroxyapatite, there was no significant change with the mechanical properties, and because human cancellous bone has yield compressive strength from 3 to 20 megapascal, we concluded that we can use this porous magnesium for had a sufficient strength for the cancellous bone applications. And this is the SM image of the hydroxyapatite coating. And as we mentioned before, you can see the needle-shaped hydroxyapatite on the surface of porous magnesium uniformly, as Hiromoto mentioned. And the coating layer was about 2 micrometers. And we performed the corrosion test, and we immersed the bare porous magnesium and hydroxyapatite coated porous magnesium into the simulated body fluid. And we checked the pH, monitored the pH change. As you can see, the corrosion was being very decreased after the hydroxyapatite coating. And we performed the cell test in vitro. We saw the SM image of the attachment of osteoblast cells on bare porous magnesium and hydroxyapatite coated porous magnesium. On the bare porous magnesium, cells didn't attach and died after 1 day. But however, on the hydroxyapatite coating one, the cells attached very well and spread had a very good morphologies. And for the conclusions, porous magnesium was fabricated without oxidation or carbonization by spark plasma sintering method. And porous magnesium has suitable pore size and interconnectivity and mechanical properties for bone implants. And corrosion resistance of porous magnesium improved after hydroxyapatite coating by aqueous treatment, and also biocompatibility has been improved. For the acknowledgement, I thank to the Professor Hyunhee Kim in our lab, SLIM lab in Seoul National University in Korea, and members of our labs. And our lab works on the hybrid biomedical implants, with mainly about surface modification and fabrication of porous implants, and also hybrid membranes. Thank you for your attention.
Are there any questions? So I wonder if you have considered doing any sort of polarization testing, electrochemical testing to compare the rates of corrosion more quantitatively.
Yes, in our lab, other people do that experiment with the dense magnesium substrate, but we found that it was a little hard to do the experiment with the porous ones, so we had to do the corrosion test with the other experiments.
And could you tell us something about the grain size of your magnesium particles?
For the grain size, first thing the important part was to fabricating porous magnesium, so we didn't see the grain size yet, but afterward I think we're gonna see the grain size and those stuffs. Yeah.
Okay. And then just finally, in your compression testing of the hydroxyapatite coated materials, did the hydroxyapatite break free? Was it relatively easily fractured off of the magnesium?
There was no result, but what I see after the experiment, I couldn't see the fracture of only the coating part, and it was hard to see the fracture of the debris of the hydroxyapatite coating. I think it breaks out with the total part of the magnesium together. Yeah.
Okay, let's thank our speaker again. Thank you. Well, that concludes our session this afternoon. Thank you, everyone, for coming, and safe travels home. I guess we have one more session after this, so thank you.